particular nature of phase transitions in metals. So these are systems where you have a conduction of electricity, and in a quantum system you also have a Fermi surface. So I just want to highlight some of the important issues and some of the standard theory of phase transitions and Fermi surfaces, and then go into more modern developments. Okay. I'm a little bit unsure of what your background is, so I presume you've all taken some many-body physics course, like Better Molecular or something? Yes? All right, good. If you have, don't worry, please just ask me questions. So first let me say a few basic things about phase transitions. So both classical and quantum phase transitions are generally understood by the concept of symmetry breaking. So you have some global symmetry in your Hamiltonian, and you vary some parameter. So in classical phase transitions, this parameter could be temperature. In quantum transition, in some term in the Hamiltonian, you change the coupling G. And then as a function of G, you have two phases. And in one phase, you have symmetry broken. And in the other phase, the symmetry is not broken. It's preserved. So there's some order parameter, which let me just call now psi. We'll look at lots of examples soon. So say here psi is not zero. If I'm thinking about a quantum system, then in the ground state. And then here psi has no condensate, and its expectation value is zero. And there's some global symmetry, like spin rotations is what we consider, where which is broken in one phase and not the other. Now once you know this, there's a whole elaborate machinery of understanding the nature of the phase transitions. I won't go into that here, and what the nature of the critical properties are. That also I won't very much talk about in my lectures. My focus is really on the two phases, and answering questions of the type, if you give me some Hamiltonian, can I tell in advance that there must be two different phases and must be a phase transition between them, or not? So that's the type of question I want to ask, not so much about what exactly is going on at the critical point. That's a much more subtle and difficult question that you answer secondly, after you answer the first question. Is there a phase transition? So Landau answered in some way the first question in the following manner, that if you have some global symmetry and in some region you find that the global symmetry is broken, other region you find it preserved, then you know there must be a phase transition between these two phases. There could be more than one, they could be first order, second order. These are all more precise questions that you can ask afterwards. But once you know this, that there must be such a phase transition. So the focus of my lecture will be really about cases where this is not true. That you find one phase here and one phase here, and they have the same symmetry, the sense that all global symmetry have the same status. But you can still argue there has to be a phase transition. And that's what I want to give you examples of systems where initially it looks like there's no possibility of, that the symmetry doesn't tell you whether there should be a phase transition or not. Landau is of course completely correct. If symmetry is broken here and not broken here, there must be a phase transition. That's not false. But there could be phase transition for some other reason. It doesn't rule out there could be some other criteria. And those criteria today we call topological criteria or topological order, and that's what I want to get into. Okay, so that's one basic fact number one. Basic fact number two, I want to talk about quantum systems, and especially quantum systems with fermions. And fermions naturally form states that don't have any broken symmetry because they form a Fermi surface. If you have systems of bosons, they usually both condense, or they form a solid, which sometimes also breaks symmetry. But in fermions, there's another very important theorem called the Luttinger theorem. So let me just also mention that. So if you have a system of fermions, which says that if you have some Hamiltonian with some fermions with some kinetic energy plus interactions, example. Then the ground state of this Hamiltonian can have a metallic ground state or a Fermi liquid in which there's a Fermi surface. This is Fermi surface. And if you look at as a function of momentum k, then in the free Fermi system, of course, all states are occupied here and empty outside. And that's the Fermi surface, that's the boundary between the occupied and empty states. Now, when you have the interacting system, that's no longer true. There are also states over here that's occupied. But the idea of a Fermi surface still holds. It's a very precise concept. Again, Landau wrote some important papers on that. And if you look at Nk, which is the number of fermions per momentum, k, there's some function, but it has a discontinuity. And this discontinuity here, kf, it defines the kf over here. Okay. Now, if you're in free space, of course, this is an exact circle or a sphere. But in a crystal, it can have very complicated shapes. And I'll show you some of those shapes later in my lectures. But you can still define the position of the Fermi surface for each direction by looking at the discontinuity in the fermion occupation number. So this discontinuity is less than 1, but bigger than 0. Okay. So the basic theorem is that with all kinds of interactions, first of all, there is a Fermi surface, which separates the inside and the outside. And then the volume enclosed by the Fermi surface, so that's the volume here. If I ignore spin and other things, which I'll just, for simplicity, I'll ignore, the volume enclosed by the Fermi surface is just the density of fermions. And now there's some, and you divide it by h pi cubed. So you take the phase space volume, this has units of inverse length cubed, and that's equal to the density of fermions, which also has units of inverse length cubed. Now there's additional factors of 2 depending on spin, whatever. So this is another very basic theorem of condensed matter physics, which says for arbitrarily strong interactions, the precise statement is that for arbitrarily strong interactions, as long as you're adiabatically connected to the free particle limit, then the volume of the Fermi surface must obey this theory. So all of density functional theory, all of the calculation of density functional theory always obey this relation. You don't even feel like mentioning it because it's just built into the whole structure of the theory. All right, so this is another very basic theorem. And I want to look at situations where both this issue and this issue play a role. So let me now describe a situation where the volume of the Fermi surface can change. Okay, so how can the volume change if it's constrained so strongly by this theorem? So now what I should have mentioned here in the precise statement of the theorem on a lattice, that this is not strictly exactly true. So if you have a metal like copper or sodium or something, well, sodium has 21 electrons, and you don't count all 21 electrons when you look at the Fermi surface of sodium. You only count 1 electron per sodium, the valence electron. The core electron you don't count. So formally the statement really, this is not strictly true. So I don't have space on the board, but let me put this here, modulo filled bands. So if you have a lattice, then you can have filled bands, and that doesn't count. You only take the partially filled bands, and then the volume of the Fermi surface, which must be in a partially filled band. I mean, you can't have a Fermi surface in a band that's filled, so there's no discontinuity of N of K. Is equal to density of fermion, but after you remove all the filled bands. So this caveat gives you also root for changing the volume of the Fermi surface, which is very important and seen in many experiments. And that's the idea of translational symmetry breaking. So if you have a particular type of symmetry breaking in which you change the size of a unit cell, then what's a filled band and what's an empty band becomes a little bit different once you change the the size of the unit cell. And so that allows you to change the volume of the Fermi surface. So let me give the most important example of that, which is antiferromagnetism in the Hubbard model. So let's consider a very particular model, the Hubbard model, which will play an important role in many things I say. So let's say on the square lattice, where you have sum on k minus t. Sorry, let's take, well, you want not just nearest neighbor hopping, but generic hopping, Wij, C dagger, I. Now I do want to worry about spin here. Let's say push roll in my consideration. That's u, sum on I, up. All right. So if you just do perturbation theory in U, you get, here's your square lattice minimum zone, and you get some Fermi surface. It's not a circle, but it's some shape here. And for the cube rates, this is actually centered at pi pi, but let me not worry about those precise details. But roughly speaking, this is 0 and this is pi. The cube rate, this is really holes and electron. This is empty and that's holes. But okay, it doesn't matter very much because everything is modulo everything. So if you have a single band on the square lattice in the cube rate, you have at large enough doping, you have a large Fermi surface vector. And the volume enclosed by the Fermi surface must be equal. So in this region here, the volume enclosed over 8 pi cubed. Okay, this isn't, sorry. 8 pi cubed is in 3 dimensions. In 2 dimensions is 4 pi squared, and a factor of 2 pi spin. And that's equal to the doping density, which we call 1 plus the density of fermions, is typically written as 1 plus p. That's how we call it. If p equals 0, it's a half of k, where you have the insulator. All right, those details are not important right now. Okay, so this is the statement that perturbation theory in U gives you such a Fermi surface. So now consider, so this is in the ordinary metal. Metal or Fermi liquid. So now consider a situation, I'm going to have to choose the next code for that, where you have spin density wave or antiferromagnetic order in a density wave. We call it SPW or antiferromagnetism. So we have this order, and so this means that if I look at the spin density, C dagger sigma I, C I. So this is just the density of spins on any side I. Now this should be translation invariant. In fact, it should be 0 by spin rotation invariance. But in the order phase, we'll call this a vector, n, some vector n, which has some dependence on I, and the dependence that I care about is the antiferromagnetic, just for simplicity, Ix plus Iy. So this has wave vector pi pi. So imagine basically on the square lattice that you get these moments on the square lattice, which have the arrangement of a chessboard, where this is up, down, up, down. So this is the two traditional proofs of that is antiferromagnet on the square lattice. So now n is 0 up here, in this phase here. Here n is 0. But now I want to ask, what is the Fermi surface when n not equal to 0? Yeah, that's it. N is itself an expectation value, so to be precise, there is no expectation value. surface in a metal when you break translational symmetry. All right, so this is, of course, an interacting system. And in fact, this actually does happen in the electron lobe qubits especially, where there's clear experimental evidence of precisely this happens as you vary the value of T. When you get T closer to 0, then you do have the formation of antiferromagnetism. And I want to know what is the nature of the Fermi surface. Now, I don't want to compute it precisely, but I want to make general statements. In particular, what is the volume enclosed by the Fermi surface? Is it still equal to 1 plus T? And the answer is no, it isn't. And the reason it's going to be different now is because you've broken translational symmetry. Entirely because of this factor here. This is not translationally invariant. So your Brillouin zone is changing. And your Brillouin zone is halving, even your unit cell is doubling. And that change is what's a filled band and what's an empty band. So how does this work? So one way to work this out is to just rewrite Hamiltonian. You can first of all do just Hartree-Fock theory. But for future purposes, let me try to do it using a pantechnical formalism, where you do what's called the Hubbard-Tutanovich decoupling of that term. So, or you can think of it as, if you don't want to invoke pantechnicals right now, just think of it some kind of Hartree-Fock decoupling. So what you do is you take U and I up. Okay, so this can be rewritten as at least an output. Let me see if I have this here in my notes. All the right factors. No, I don't. All right, so I'm going to just ignore this rotational invariance and just treat the z-axis as special where it's easy to work out. So this I can write roughly as, approximately as u ni up and ni down plus u ni down and expectation of ni up. Now expectation of ni up and ni down will have this kind of oscillation because this is just ni up. And this is equal to ni up minus ni down, at least the z component of n. So they're not equal to each other, and they oscillate. So this will have a term which is, I think, 1/2 u over 2 times nz times ni up minus ni down, and minus 1 to the ix plus i1. Okay, so this is one contribution in a phase where you're broken the symmetry. There will be an effective potential for the fermions, which is staggered, and has the opposite sign for up and down space. Right. So if I write this in momentum space, this is equal to something like, again, I don't care about all the factors, it will be basically some factor of nz up front, and sum on k, and it will be c dagger k up, times c k plus k up, minus up goes to down. So here, k, capital K, is this way right here. So this term here, because of this factor, it scatters an up electron, it changes the momentum of the up electron by pi pi. Okay, let's do the Fourier transform of this term, and I up times that, and you just get this. Okay? So that's the most important result, and once you have broken translational symmetry due to the antiferromagnetic order, the momentum of the electrons is not conserved. Is only conserved modulo capital K, where K is pi pi. Previously it was conserved modulo 2 pi 0. Now it's conserved only modulo pi pi, which is a smaller wave vector. And then square root of 2 that the previous one, that's 2. So that has reduced the size of the Brillouin zone. So if I now go to momentum space and rewrite the Hamiltonian for the electrons, then so the effective Hamiltonian sum on K, C dagger K. Let me for upspin, so this is for, and similarly for downspin. So C dagger K, C dagger K, K, oh sorry, epsilon K. And then you'll have also sum on K, let's just separate them out. Epsilon K plus pi, K plus K, C dagger K, K plus K, K plus K. I'll put a prime here, and the prime means that the sum now is over a smaller Brillouin zone. So this was the original Brillouin zone. This is from 0 to 2 pi. Well, I put a 0 here, then this is pi, this is minus pi. But now the prime means I'm summing over this zone. I'm summing over this region here because momentum is only conserved modulo pi pi. So this is the reduced Brillouin zone. So when I sum over this and I sum over this, I effectively sum over the entire Brillouin zone. So this here is just exactly equal to the first term over there, written in the reduced Brillouin zone. Now the reduced Brillouin zone is very useful because of this term now here, which I just put in. This will be something like n z, or I'll assume this in the z direction, times sum on k, again in the reduced Brillouin zone, C dagger K, K plus K plus C dagger K plus K, C K. All right, so this is the world's easiest Hamiltonian to diagonalize. It's just a 2 by 2 matrix. You can just diagonalize it in your head. And so now you know the eigenvalues. There are two eigenvalues, Ek plus minus. They're going to be equal to Ek plus Ek plus K over 2 plus or minus square root of Ek minus Ek plus K over 2 whole squared plus Mg squared over the factor of u here, or u over 2 that I forgot. So it's, you know, yes.
You have only understand why
This one? This? Yeah. So this is summing over this region. Because the primes, little k goes over this region inside. Then k plus k goes over these regions. Sorry? No. This is just, I haven't told you where the Fermi surface is. It's just the dispersion. I will put the tangential potential wherever you want. Yeah, so the original Hamiltonian, so this plus this, so these two terms is equal to sum on k, epsilon k, sine k, k. There's no prime. This is just equal to this. I've just written this big sum as one term here and one term here. Okay? So you can just check that. Of course, you have to take this Ek is periodic. So of course, I'm using the fact that Ek plus 2 pi 0 is equal to Ek. That's always true. I need that. And once you use that, then this is just the same. And so now the reason for writing it like this, with using a reduced Brillouin zone, is that the Hamiltonian have the sum over everything is exactly the same, so I can pull it out. And now the Hamiltonian is just a 2 by 2 matrix, and these are the eigenvalues. Okay, so now we just have to fill the bands. It's a little more complicated. You don't have to fill one band, you have to fill two bands. And you can ask what happens. Okay, so let me try to do that. Let's do it over here. Because I'm still talking about. So that's the question. What is the Fermi surface? So you can do this calculation, right? You just give it to your computer, take some epsilon k, compute this, and fill the bands and see what happens. But it's easier to see on a picture. So what happens in a picture? So here, let me draw show you pictorially what happens. So here's the original Fermi zone. This is where I could have used some slides, but okay. So my original Fermi surface, let's use a different color here. So this is my original Fermi surface. Say it looks something like this. So this is the original Fermi surface where epsilon k equals 0. So that's what I start with. And now it's going to mix with epsilon k plus k. So let me draw epsilon k plus k. So that if I shift this by k, I'm going to get another Fermi surface. This is going to be centered at this point. So let's see if I can draw that well. So there's another Fermi surface here, which looks something like this. Okay. So this is the line epsilon k plus k equals 0. There's of course a similar copy here. There are 4 copies of it. Just draw some of them. Similarly here, and here, and here. Okay, so now I have 2 bands, and I should only look, inside this zone. But I've just drawn it in the extended zone scheme. So now what happened? Well, it's complicated, but one interesting point to look at is exactly this point. So at this point, both are 0. At this point, both epsilon k is 0 and epsilon k plus k is 0. So this formula becomes very easy then. This is 0. This is 0. So there are 2 eigenvalues with plus or minus u. There's nothing at 0. So at that point, you have a gap. So you open up a gap at this point, and that's the most important thing. So this can't be the full line of ek cannot vanish. So this point here, at that point I know that ek plus minus, which is the real dispersion, cannot be equal to 0, even though both epsilon k and epsilon k plus k are 0. So that's basic fact about degeneracy. When you have a degeneracy and you couple them, they split. So that's what this antiferromagnetism does. It couples the states, the 0 energy state, on the Fermi surface because of the antiferromagnetism. So now it's easy to figure out. So what is the line over which ek is 0? So now this is not too large. You can see what it's going to do. Basically, you're going to open up a gap. But once you move away from here, then either epsilon k or epsilon k plus k is non-zero. So this, if u is small, this won't matter very much. This only matters when both are 0. So that means that I need a third color. This is white. Well, okay. Let me try. So that means the actual, let me draw it here. There's this region here, and there's a region here. And so this line here now, this edge of this region, this line and this line are ek plus minus. So that's the actual Fermi surface. So what's happened is that what the original purple Fermi surface, which is called the large Fermi surface, has reconstructed into small Fermi surface or pockets. These pockets here. And a similar one here. It's basically very much like level repulsion. You move the Fermi surfaces away from these points, and then everything else shrinks. Okay? So this is now much smaller Fermi surface, and that seems like schemes in bilays of Luttinger theorem, but what comes to the rescue is modulo filled bands. Now in fact, since the Brillouin zone is half, there's a one filled band sitting there, which is partly in EK plus and partly in EK minus, which has exactly one electron per side. So in this new state, in the ASCII double state, the volume of the Fermi surface, and I'm being a little sloppy with factors of 2 and so on, and 2, and this volume has to be measured in the Brillouin zone, not outside the Brillouin zone, is equal to not P, 1 plus P by T. So, and this P measures the sum of all of these. Now, there's a little subtlety here which I've put under the rug. This is actually a whole line, this is electron line. So P is actually this plus this plus this plus this, minus this, minus this, minus this, minus this. Which is, one of which had EK plus negative inside and positive outside and so on. All right. So the point here is that there's a broken symmetry. Because of a broken symmetry, the Brillouin zone is half. So the number of electrons per unit cell has to be counted modulo 2. Now the unit cell is doubled. So that's another way to think about it in real space. Here, this is 1 plus P is the number of electrons per unit cell modulo 2. Because you can have each filled band of copper has many, many electrons. You don't worry about those, all the 4 electrons. So now what's happened is that at 1 per side, this is 1 per side. But now in the new state, there are 2 sites per unit cell. The anti-ferromagnet has 2 sites per unit cell. I erased it. So the 1 per side becomes 2 sites per unit cell, 2 electrons per side, and that you can draw. So that's like a filled band. So when you double this, that 1 drops out, so the P is left over. Okay. So it's modulo 1 when the size of the unit cell is 2. Anyway, so this is the new relation for the volume of the Fermi surface, and you can easily verify this from this dispersion that this is good. Okay. All right, so that's the main lesson. When you have a broken symmetry, the Fermi surface can change in volume. But not to worry, the Luttinger theorem still obeys. When you look at the precise statement of the Luttinger theorem, it's a statement about per unit cell modulo filled bands. When you take that into account correctly, the Luttinger theorem is still obeys. All right, so then I can draw another figure over here to complete this this thing. Let me just expand this a little bit. So if I was considering a metallic system, I now say this is U, or sorry, U is the other way. So this is U. And this I'll call N. So the symmetry here is spin rotation symmetry and translational symmetry that is broken by the antiferromagnet. And in the symmetry preserved state, here the Fermi surface looks like this. And in this phase, with the symmetry broken, the Fermi surface has these pockets. This is the Fermi surface. And the Luttinger theorem, Luttinger is okay here, and Luttinger here also is also okay, because the bulk unit cell is double. So, the Luttinger theorem is quite subtle, and it's very precisely stated. When you take the precise statement of it, then it's obeyed in both phases, but you have something else happening. When symmetry is broken here and not broken there, the Fermi surface is changing. And that's not something that can happen otherwise. And Luttinger taught us that the volume never changes, no matter how strong the interactions. But it can change if you break a symmetry. And this kind of thing has been observed many times in many experiments, especially in the electron cuprates, also in the pnictides, and so on. There's various more complex versions of this kind of changes of Fermi surfaces due to presence of broken symmetry. All right, so that was all an introduction. Already taking 45 minutes. But any questions? Who are happy with that?
Symmetry program.
Yeah.
So the order is represent that the Fermi surface become discontinuous. The Fermi surface become.
Yeah. It has many pockets, so it has different. Yes. Yeah. The disconnected pieces. That's all right. Luttinger theorem still applies. You have to. It still applies because you have to account for the modulo for unit cell, 2 electrons per unit cell, or modulo fill bands. And this would be the statement, EFS is the sum of the disconnected pieces. And actually the area comes with a sign, whether it encloses holes or electrons. So you have to take that into account also. Okay, there's a question back there. Yeah.
Is the broken symmetry global or local?
Oh, this is global. I'm only talking about global symmetries. Yes.
So both of them are global.
Yeah, global. I will turn to local symmetries very shortly. But I prefer not to call them symmetries because local things they're more like constraints rather than symmetries. This is a global symmetry, which is broken in an antiproton. Yes?
So why do you drop the spin gradient here?
The spin what?
The spin gradient, the spin up and spin down.
Oh, I do the same thing for down. I just put this is the Hamiltonian for up electron. You do exactly the same for down electron, just the sign will be different. But that won't make any dispersion change to the dispersion. The dispersion will be the same. Okay. The waveforms are slightly different. Other questions? All right, so that's the introduction. This is what happens, and this is, as you see, an intimate connection between symmetry breaking and phase transitions. And we've also seen that the intimate connection between symmetry breaking, especially translational symmetry breaking, and the Luttinger theorem. That allows you to reconstruct the Fermi surface. Okay, so the rest of my lectures will be about other cases. Is this the whole story? Can there be other things? And this is what I want to show you. So if I draw this a little bit more anticipating. So there's what I will show you. Well, let me draw it this way. Okay, these phase boundaries are just approximate. There's going to be another parameter here. I won't tell you. I'll tell you eventually what this parameter is. Let's call this K. So now this is a two-dimensional phase diagram, and I'm going to find a phase here where you're going to violate all of these standard things. So this phase here will have topological order. And here, so the symmetry is preserved, no symmetry broken. Symmetry preserved. N is equal to 0. But the Fermi surface will be small. So the Fermi surface will look like this. And so the Luttinger theorem, is not obeyed. Okay, so it's like a mixture of these two. So the symmetry is not broken, but the Fermi surface is like this, and this will be a Luttinger. So now we have different types of phase transitions. So this transition here is the conventional transition. This is a symmetry-driven transition. So this is symmetry, broken symmetry transition. Symmetry phase transition. Well, this transition here now is something very interesting. It will be a topological phase transition. Because symmetry is the same on both sides, but topology changes and Fermi surface changes. The symmetry remains exactly the same. This is in some ways the more complicated, in some ways the simplest. They both happen, both symmetry and topology change. And I want to show you an example of this and say some things about these types of phase transitions. Okay. Now, of course, we're talking about such phases mostly for the fun of it, but not entirely. There's been a lot of indication from experiments of the whole lobe cuprates that some such thing is happening in the pseudogap phase. So this will be our starting point of the theory of the pseudogap phase. And there's some very new results from ZX10 that I hope to show you tomorrow, or maybe I won't get to it today, where there's some support for exactly this type of phase, direct support for this phase. But let's put that aside. Let's try to now talk about this structure of phase diagram in other models where you have both symmetry breaking and topological phase conditions, and maybe even the two together. Now I should clarify here before what I mean by topological phase. The word topological is everywhere these days, especially after the 2016 Nobel Prize. There's many, many different kinds of topology, and it all gets very confusing, even for me who's been in the field for a long time. People use the term all the time. So way I like to think of it, there's two distinct ways we talk about topology today in physics. One is the topology of, let's say, the integer quantum Hall effect. So what is the integer quantum Hall effect? Well, the integer quantum Hall effect happens when you have free electrons, essentially, moving some potential in the magnetic field. And the integer quantum Hall state in the bulk of the sample has nothing special. Before emission or tunneling in the bulk of the sample, inside the sample, you will just see electrons. There are only simple electron excitations with a gap from one Mandel level to the next. But if you look at the edge, there are these protected edge states, which, no matter how strong the disorder, are there, and they're responsible for the quantization of the Hall effect. All right. So the Hall effect, the integer quantum Hall effect, was the first to be discovered, I guess, in 1982. And for a while it was thought, for a long while it was thought, it's something special to high magnetic fields. And then through various works, including Harlane early on, and then especially Charlie Kane and Eugene Millet pointed out that you could have the same structure, that is a trivial bulk with protected edge states, even in systems with preserved time reversal, symmetry, and which have no magnetic field. So that's those kind of states of topological insulators and topological superconductors that there's so much work about today. People looking about Dirac edge states and other funny things happening on the edge, but nothing funny in the middle, are descendants of the integer quantum Hall effect. So that's one type of topological phase and topological order and topological phase conditions, which there's a lot of work on. And generally, all of that work essentially is theory of free particles. It's subtleties of the global structure of the wave function of free particles. This is not that type of topology, although this type of, the word topological order here is older, but it's been transferred to the other type. So this type of topology is like the fractional quantum Hall effect. So the fractional quantum Hall effect has many properties that are all mixed up. But the property I want to focus on is that in the bulk of the sample, there's fractionalization. There are Laughlin quasiparticles, which carry charge 1/3 in that case. So there are bulk excitations that cannot be just made up of electrons. You can't inject a Laughlin quasiparticle from the outside into the bulk. And sometimes, so another way to say it is there are excitations in the bulk of a fractional quantum Hall effect that cannot be created by any local operator. No matter what you do, by any physical operator you can make in the laboratory, you cannot create one quasi-particle. You will always create 3 of them for the U equals 1/3. And then you can separate them far away, infinitely far away in principle. You can't create one of them. So there are these protected excitations that cannot be created by any local operator. That's what I mean by topological order. Now, the fractional quantum Hall effect also has edge states, and that's the confusing thing. The things I'm going to talk about here have no edge states. At least the examples I'll give of topological order. So this particular state has nothing special on the edge, but it does have some rather strange looking excitation in the bulk, which would be very hard to detect directly, but hopefully someday things like that can be detected even in zero magnetic field. Now there are some indications in some, things like tangle antiferromagnets So you have spin liquid states where there are some indications of such indications in the bulk. But that's much, in some ways, that field is a little bit behind the other kind of topological order of the King-Millet type, which has vector excitations only on the boundary, but not at the boundary. Okay, so that's just a little aside in case you got confused by what I mean by topology. I'm really mean here topology like the fractional quantum Hall effect, but with time reversal symmetry. Okay. All right, so now I'm going to start talking about some models that introduce the idea of topological order, but contrary to where you probably have seen it or heard about it, there's going to be no edge states, there's going to be no magnetic fields, there's just going to be spins interacting with each other. Okay. And time reversal symmetry will be preserved everywhere. So there is a very simple example, and in fact it's the earliest example of a topological state. That's the discrete gauge theory of Wegener, and I'll just describe some of its properties in a modern language, and then show you how that kind of topological structure is very useful in even thinking about things like this and what happens perhaps in the Hubbard model. Okay. Any questions on that? All right. So I have to end the 4:30 here, so we'll take them. All right, so let's get started then on the main part of my lectures, which is, let's talk about Z2 gauge theory, or Z2 gauge. So this is a, I'll start with a model which seems to have nothing whatsoever to do with the Hubbard model, and has many artificial features and seemingly huge amount of symmetry, local symmetry. So it seems, how could this possibly have anything to do with the Hubbard Hamiltonian? And I'll consider my lectures a success if at the end you can see that it does have something to do with what I've said so far. Okay, so let's just talk about, let's step back now and just talk about a model for the fun of it and study it. So the model is the Z2 gauge theory. And I'm going to be in 2 plus 1D on the square lattice. Which turns out to be the most interesting case. And some of what I've said, but not most of it, it goes back really to 1972 with the Wegener. All right, so the Hamiltonian is defined on the square lattice. And of course, today, most of you, I imagine, are familiar with the toric code, which is a solvable version of this. But I want to talk about Wegener's original formulation because it actually has a phase condition. Solvability is nice, but not if it just puts you in a regime that doesn't tell you about the full phase diagram. I want to study the full phase diagram, and so then we go back to Wegener. So like the toric code, the degrees of freedom here, or I should say the other way around. The toric code has degrees of freedom very similar to Wegener's Z2 gauge theory. Spins on the links of the lattice. So there's on each lattice side, there's a spin that can point up or down. Okay. So there are spins. So there are operators that act on these 2 states, which are called sigma x and sigma z. And on every, so these operators sit on every link. All right, so what is the Hamiltonian? The Hamiltonian has a flux term, sum over all plaquettes, product on every link belonging to the plaquette of sigma z on that link. So just take the product of sigma z around the plaquette, and this term is also there in the toric code, which is the product of sigma z on every plaquette. Okay. So that's the flux term. And then there's another term which I'll call G, and then we call it KG, yeah, G. Sum on all the links of sigma x L. So So this is not in the toric code, and it's just a field acting on every element this way. All right. So that's the Hamiltonian. It's a very simple looking Hamiltonian. It has a very interesting phase transition, which really was Wegener was thinking about quark confinement in quantum thermodynamics, and this was his model of a confinement phase transition between free quark and confined quark phases. This model, unlike QCD, has a phase transition. Pure QCD is always in a confining phase. This has both confined and deconfined phases. Okay. Anyway, so that's the very simple model. It's not exactly solvable. Almost certainly, no one's ever going to solve it exactly, because it has a non-trivial phase transition, strongly coupled phase transition in it. But we can understand a lot just by looking at what happens for small g and large g and just studying the phase diagram, which is all I'm going to do. All right, so that's the Hamiltonian, that's it. Okay, well, I haven't fully specified it. To fully specify it, I have to take into account the fact that there's an infinite number of operators that commute with the Hamiltonian. And there's an operator you can define on every site I, so this is the site I, this I call the links. So there's Gi on every I. There's a product of the links belonging to the site I. These are all four links that come to the end of site I, times sigma x on these links. So if you take product of sigma x, sigma x, sigma x on these four, that commutes with the Hamiltonian. So you can easily check that. Obviously it commutes with this, and it commutes with this because every cross, when it intersects with every plaquette, either intersects in two places or not. You take this plaquette and that cross. Either case they commute because the sigma is anti-clockwise. All right, so this Gi has the property that the Hamiltonian H Gi equals 0. And so now Gi squared is 1. So its eigenvalues can be plus or minus 1, and I'm going to fix them to be plus 1. So this is the Gauss law. So you can think of this as an infinite number of symmetries because you have an infinite number of disturbed quantities, but that's really not the way you want to think about it because you're going to fix Gi. It's not a, so every state, no matter what state we talk about, Gi acting on any state, any valid state is the state itself. So unlike a symmetry, if I take some operation of a spin rotation, you give me a wave function, I'm going to rotate the spin, I get a different wave function. It's a different state, which is an allowed state in the Hilbert space. Here, I'm not allowing that. I'm just saying this is my Hilbert space where Gi is just 1. So it's not really a symmetry. It's more like a Gauss's law constraint case. So there is no symmetry in the Hamiltonian. Once you impose this constraint, there's no other operator. There's no discrete symmetry at all. So there's no possibility of a broken symmetry. Yet it has a phase transition. So really Wegener, already in 1972, discovered really the first model of a phase transition without a broken symmetry. And he interpreted it in terms of confinement, deconfinement, which I won't use. Today we'll say what he discovered was a topological phase transition. So one phase has topological order, other phase doesn't. Okay, so let's try to understand this. So what are the two phases? Yes. Yeah, so 4:30 I end, right?
No, 4:30 you end this.
Yes, I know.
45 minutes.
Yeah, so let me just say a few things and then we'll take a break, yeah. Just finish this train of thought, thank you. So let me at least write down, what happens. So let's just look at G much, much smaller than K. Then what you want to do is minimize the flux. So this is a negative K positives. And so this has to be +1. And it will be +1 if you put all the spins on. So then my ground state, well, let me call it the ground. Yeah, okay. This G is not to be confused with that G. Let me call it size 0, the ground state. It is the state up, 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 up. Everything is up. But that doesn't obey this constraint, because if you hit GI on this, you get a different state. But it's easy to fix that. You just put a product on I, 1 plus GI here, and that's good. Now you can check, because of GI squared equals 1, that this is still true for this state. So then that's the unique ground state in this limit, and the infinite lattice on V is much more smaller than state. Now, what are the excited states? Well, so clearly what we have to look at are the fluxes through each limit. So in this case, so if I take the blue perturbation theory in G, what that's going to do is flip one spin. So if I flip this spin, so let me just draw a line on this flip spin. So that one flip spin is flipped, and all the other spins are up. Then this flux, there's a flux here of +1, so this costs you energy 2K, and this costs you energy 2K. So you have these two objects over here. And then now this, you try to go to higher order, you flip a few more spins. And then what can happen is you can flip this one, and now this costs you energy 2K. This doesn't cost you any energy because the flux is still +1, and so on. So you can keep moving that. So what happens is now you've created two excitations, one here and one here, and they can each carry pi flux, or -1 flux, and they can move far apart. So those are the excitations. These sometimes called the M particle, the toric or the boson, or pi flux, or -1 flux. This is equal gauge theory, and these can behave like particles that move around and have some. Each particle has energy cost 2K, so there's a gap. So that's the topological order at one level. There's nothing you can do to create one particle on its own. Any operator will create them in pairs. So once you create them in pairs, you can separate them. So this phase is topological. All right, I'll just stop there. Let's take a break and you think about that.